Hello everyone. Today I'll be talking about generalization bounds for learning with linear and quadratic side knowledge. My name is Teja Bandula, and this work is joined with Cynthia Rudin from MIT. Motivation. For many applications, the amount of domain knowledge we could potentially use within our learning processes is vastly larger than the amount of domain knowledge we actually use. There are a couple of compelling reasons for this. First, analyzing an arbitrary type of domain knowledge is hard. Most domain knowledge, that is not sparsity and smoothness, is not easy to study. The second reason is that the domain knowledge can be very problem specific. It may be too specific to the domain to have an overarching theory of interest. We provide theoretical guarantees for a large class of problems with a general type of domain knowledge that goes beyond sparsity and smoothness in this study. The setting we will be concerning ourselves with is a supervised learning setting. We have an additional set of examples without labels. We have prior knowledge about the relationship between their unknown labels. In this context, we consider two types of knowledge about the unlabeled examples, leading to linear constraints on a linear function class and quadratic constraints on a linear function class. Pictorially, you can think of a linear constraint as a half space intersecting with a function class represented as a circle here. And pictorially, you can think of a quadratic constraint as an ellipsoidal constraint intersecting with our original function class here. This intersection shrinks our function class and thus may affect generalization. And so is the case for the quadratic constraint. In our setting, the training sample will be represented using xi by I, and there will be n quantities in there will be n such examples. The unlabeled examples will be represented using x tilde I varying from 1 to m. The linear function class will be represented using script f parameterized by a coefficient vector beta. That is, our function class script f will be the set of all linear functions which is equal to beta transpose the feature vector x, such that beta obeys a q-norm constraint and potentially other constraints arising from domain knowledge. In our case, the constraints which arise are linear or quadratic in nature. So let's dive into knowledge leading to linear constraints. The first example that I want to motivate is the setting where we may have a partial order knowledge. Let's say we have a knowledge that the score of unlabeled example I is not too much higher than the score of unlabeled example j. We could also have the opposite information, which is that the score of the unlabeled example I is lower than the score of unlabeled example j. In either of these cases, we can represent our function class in the following manner. Script f is defined to be all linear functions with the usual q-norm constraint on the coefficient vector and a constraint which is a linear inequality. So for the unlabeled example I and j, we have that the score beta transpose x tilde I minus the score beta transpose x tilde j is upper bounded by constant c. If this constant is positive, then we are in the first case, and if the constant is 0 or negative, then we are in the second case. And this can be true for multiple such pairs I and j, which we represent using our set E. The second motivating scenario is when we have a must-link kind of a knowledge. In this knowledge, we want to encode the information that the score of x tilde I is close to that of unlabeled example x tilde j. We can write an absolute value constraint where we bound the absolute value of the score differences, that is beta transpose x tilde I minus beta transpose x tilde j, the absolute value, to be upper bounded by a constant. and this can be represented using two linear inequalities. A third type of scenario is as follows. In this case, we may have a sparsity like knowledge on the subset of scores of unlabeled examples. That is, we may know that only a few unlabeled examples have non-zero scores. In this case, we can have an L1 norm constraint on this specific subset of unlabeled example scores. The example scores are given by beta transpose x tilde 1 to beta transpose x tilde the size of the subset, and we're imposing a one norm constraint on it. The one norm is used as a proxy to induce sparsity here, and the one norm constraint is actually equivalent to a collection of linear constraints. Now that I have motivated a few examples of how linear constraints from unlabeled examples can arise, I want to look at the complexity of the resulting function class. In order to come up with a measure of complexity, I'll be using the notion of a covering number. Other notions such as Rademacher complexity, fat shattering dimension, VC dimension, and the like can also be used. So to define a covering number, I want to first define an epsilon cover. An epsilon cover of a set A is a finite set U such that every element of A is less than epsilon distance away from some element in U. A covering number is the size of the smallest such epsilon cover U. It is represented in our notation as n. It takes three arguments. The second argument is a set on which we are trying to find the cover. Rho is the distance metric with which we evaluate the distance, and epsilon is the parameter of the epsilon cover. If the metric rho is induced by a norm, we will use the following notation where we replace the rho with the norm Euclidean with the norm. And in our case, we will see that the set A is actually lives in a finite dimensional Euclidean space, so we'll use Euclidean 2 norm. So now we are ready to state our first result. For that, let's consider a generic function class f, which is a linear function class. Let it have a 2 norm constraint, which makes it bounded, and then which makes the parameters bounded, and let us also have a linear constraint on the coefficient vector beta. Let the linear constraint be A transpose beta less than or equal to 1, where now the coefficients encoded in A depend on, for example, some information about the unlabeled examples. Let the restriction of f, represented as script f subscript s, be a set in an n-dimensional Euclidean space, which is the evaluation of every function in our function class over the n training examples x1 to xn. Our first theorem is as follows. For any epsilon greater than 0 and sample s, we have that the covering number with a certain radius, a certain parameter for the cover, of the restriction of f in the Euclidean norm is upper bounded by a quantity which is a product of three terms. The second and the third term together give us a measure on the number of balls needed to cover the bounded set, the 2 norm bounded set in the p-dimensional Euclidean space. The first term gives us the fraction of the volume remaining after the ball is intersected with a linear constraint, which is in our case A transpose beta less than or equal to 1. Geometrically, what happens is that when we have a linear constraint and a 2 norm based ball constraint, the linear constraint splits the ball into two spherical caps, and alpha represents the fraction of volume remaining in the spherical cap after we remove the other spherical cap. Let's consider a more general set for f, where we replace the 2 norm constraint with a q norm constraint, and we also replace a single linear constraint with multiple linear constraints, in fact v such linear constraints, parameterized by parameters cj nu. In this case, before we come up with an upper bound on the covering number, we want to define two polytopes. The first polytope is an integer polytope. In a p-dimensional Euclidean space, in a p-dimensional space, its elements are p-tuple integers such that their absolute values sum up to less than or equal to k. The second polytope pck is a subset of the first polytope. It is all those points in the first polytope such that they also satisfy v number of linear constraints parameterized by c tilde j nu. C tilde j nu are related to c j nu in the sense that they are scale values. I'm not showing the scaling constant here, but these get determined once we specify our function class. So given these two definitions of the polytopes, we can state our theorem. The theorem states that the covering number with a certain radius of the restriction of f with the 2 norm is upper bounded the minimum of the number of points in the first polytope and the number of points in the second polytope if epsilon satisfies a certain inequality and 1 otherwise. So the number of points in the polytope gives us an upper bound on the covering number of the restriction of f, which is what we care about. The quantities k0 and k are given here. K0 depends inversely on epsilon square, and k is the maximum of k0, and a quantity which depends on properties of the training data and the properties of the constraints that we impose. These constraints we can think of as arising from the unlabeled examples. So let's move on to the setting of quadratic constraints on a linear function class. Let me motivate how a quadratic constraint can arise in the scenario where we may again have a must-link type of knowledge. In this case, we want to encode that the unlabeled example x tilde I and unlabeled example x tilde j have similar scores. What we can do is that we can impose a 2 norm square constraint on the difference between the scores, which is represented here using in the blue box. I have just rewritten the 2 norm square constraint of the score difference as a product as a product here in a quadratic form, so that you can see that we have a rank 1 matrix getting pre-multiplied and post-multiplied with beta and getting upper bounded by a pre-specified constant Cij. This is a rank 1 matrix. It is symmetric and it leads to an unbounded ellipsoid. Its intersection with the bounded ellipsoid will give us a function class, bounded function class, which may be smaller than the original function class. And this inequality can also be true for multiple such pairs, giving us an intersection of multiple ellipsoids. Another scenario is that of similar labels. Let's say we want to encode the knowledge that if the score of one of the example is large in magnitude, then the other example score is necessarily small. This can be encoded using a product of scores being upper bounded by a constant. This again gives us a quadratic form. Here, of course, the inner one-dimensional matrix is not symmetric. We can symmetrize this quadratic form and then verify to see whether the symmetrized matrix is positive semi-definite or not. If it is, then we again have the same situation as before, where we have an intersection of multiple ellipsoids. The third scenario where we may want to encode knowledge which leads to quadratic constraints is a setting where the scores of the unlabeled examples are related to each other in the following manner. First let me explain the constraint. The constraint is a 2 norm square constraint on the scores of the unlabeled examples. The scores of the unlabeled examples are given by a product which is xu transpose beta. This is an m-dimensional vector. It is getting multiplied with a matrix tau, and its 2 norm square is upper bounded by a constant. If the matrix tau is identity, then we have an energy constraint on the labels. This is similar to Tikhonov regularization. If it is banded, then we can encode that the variation in the labels is smoothly varying. The final scenario that I want to consider is that of graph regularization. It is, uh, it is known in semi-supervised learning. It is used in semi-supervised learning. Let's say we have the knowledge. Let's say we have the knowledge of the neighborhood of each unlabeled example. Then we can define an M vertex graph on these unlabeled examples. We can encode the knowledge that the labels should be similar to the labels of its neighbors. So the label of an unlabeled example should be similar to the labels of its neighbors. This can be encoded as a quadratic form as shown in the blue box. The quadratic form involves the graph Laplacian and the scores on the unlabeled examples. This is an intersection of two ellipsoids. So now that I have motivated how quadratic constraints can appear, let's see, I want to come up with the complexity of the resulting function class using a slightly different complexity measure, which is the Rademacher complexity measure. Again, the restriction of f on the sample, denoted as script f subscript s, is a subset in n-dimensional Euclidean space, and it is the evaluation of every function in a function class over the n training data features, training data examples. That the empirical Rademacher complexity is then defined as the expectation over the randomness due to IID Bernoulli variables of the quantity which is the supremum of f over in our function class, one of the term 1 by n times the inner product between the n-dimensional Bernoulli variables and the evaluations of the function over the training data examples. The Rademacher complexity is just the expectation of the empirical Rademacher complexity over the unknown source distribution, that is over the randomness of the sample choice. So let the abstract function class with two quadratic constraints be represented as f as the set of linear functions such that beta transpose a1 beta is less than or equal to 1 and beta transpose a2 beta is less than or equal to 1. Let the ellipsoids corresponding to each of the constraints be psi1 and psi2. One strategy is to find a tight circumscribing ellipsoid psi gamma and then find its complexity. By tight we mean that there is no other circumscribing ellipsoid that can have its boundary between the boundary of psi gamma and the intersection region. This can be characterized relatively easily if we only have two ellipsoids. If we have if we have k ellipsoids, then we will have a k-1 parameter family of tight ellipsoids. So given that we can find a circumscribing tight ellipsoid, we can state the following theorem. Let's say our function class again is an intersection of two ellipsoids. The first ellipsoid involves parameter bb and the second ellipsoid involves the matrix A2. Then our empirical Rademacher complexity is upper bounded by 1 by n times the square root of the trace of the product of three matrices. The first and the last matrices are the matrix of the training data features stacked next to each other as columns. The matrix in the center is the matrix corresponding is the inverse of the matrix corresponding to the circumscribing ellipsoid. We can now minimize this over all circumscribing ellipsoids so as to get a tight upper bound on the Rademacher complexity. When the second ellipsoid is not present, this reduces to a known result. A lower bound on the empirical Rademacher complexity can also be derived, and this is stated in the following theorem. The empirical Rademacher complexity is lower bounded by kappa by log n times the same the upper bound on the Rademacher complexity. Kappa is a parameter which depends on several constants in the problem, and it also depends on the interaction between the labeled and the unlabeled examples. Now that I have defined both the linear and quadratic constraints, I can merge uh, both the settings and define a common function class, common linear function class, which has two quadratic constraints and v linear constraints. Let the polytopes pk0 and pck be defined as before. In this case, we have the following theorem on the upper bound of the covering number of this new function class. The upper bound is precisely given as before as well, except that the constant uh, bb is changed to the square root of the biggest eigenvalue of the A int comma inverse matrix. In summary, we developed a learning theory framework for studying knowledge leading to linear constraints, knowledge leading to quadratic constraints. We bounded the complexity measures of the hypothesis space in hypothesis spaces involving a single linear constraint, multiple linear constraints, two origin-centered quadratic constraints, linear and origin-centered quadratic constraints. Our work extends learning theory to study domain knowledge beyond sparsity and smoothness. Thank you.